Welcome, everyone. I'm excited to kick off our presentation today with a fascinating topic. Today, we'll be exploring the laws of motion. This is the foundational framework that explains how objects move and interact in our universe. Over the next few slides, we'll cover the key principles that Newton formulated and see how they shape our understanding of physics. So, let's get started and dive into the world of motion. Let's explore the fascinating concept of momentum of a body. Momentum is essentially the quantity of motion an object has, which depends on its mass and velocity. Understanding this helps us grasp how objects move and interact in the physical world. Moving on to Galileo's experiment with an inclined plane, this was a groundbreaking study that showed how objects accelerate uniformly when sliding down a slope, challenging earlier ideas about motion. It laid the foundation for our modern understanding of inertia and acceleration. Next, we have the conservation of momentum. This principle tells us that in a closed system, without external forces, the total momentum remains constant. It's a key idea in analyzing collisions and interactions between objects. Then let's talk about inertia and mass. Inertia is the tendency of an object to resist changes in its motion, and mass quantifies this resistance. The greater the mass, the more inertia an object has, making it harder to start or stop. Force of friction is another crucial point. Friction opposes motion between surfaces in contact, and it plays a vital role in everyday activities, from walking to driving. It's a force that can either hinder or help motion, depending on the situation. Moving to Newton's third law of motion, this states that for every action, there is an equal and opposite reaction. It highlights the mutual interactions between objects and explains many phenomena, from rocket propulsion to walking. Next, Newton's first law of motion tells us that an object will stay at rest or move at a constant velocity unless acted upon by an external force. This law introduces the concept of inertia and forms the basis for understanding motion. Then, Newton's second law provides the mathematical relationship between force, mass, and acceleration. It shows us how the acceleration of an object depends directly on the applied force and inversely on its mass. Now, let's consider the difference between balanced and unbalanced forces. Balanced forces do not change an object's motion, while unbalanced forces cause acceleration or deceleration, leading to a change in velocity. Finally, Newton's laws of motion are the fundamental principles that describe how objects move and interact. They are the cornerstone of classical mechanics and help us understand everything from everyday movements to complex celestial phenomena. All these points connect to give us a comprehensive understanding of how forces influence motion, which is at the heart of physics. Let's talk about force. Essentially, force is an external effort that can do several things to a body. It can move a body that's at rest, or it can stop a body that's already in motion. It can also change how fast a body is moving, either speeding it up or slowing it down. Additionally, force can alter the direction of a moving body, making it turn or change course. And it's not just about motion. Force can even change the shape and size of a body, like when you squeeze or stretch an object. So, in simple terms, force is a powerful external influence that can cause a variety of changes in any object or body. This understanding of force is fundamental as we explore how things move and interact in the physical world. Now, let's explore how force can affect a moving body. First, force can change the speed of a moving object. For example, pushing a swing harder makes it go faster, right? Similarly, force can also change the shape and size of a body. Think about kneading clay or stretching a rubber band. That's force at work. Next, force has the power to stop a moving body. Imagine catching a ball. You use force to bring it to a halt. It can also change the direction in which a body is moving. If you steer a bicycle, you're applying force to turn it around. And importantly, force can move a body that is at rest. If you push a stationary chair, it starts to move. That's force making it change from rest to motion. These effects of force are fundamental because they help us understand how objects behave, whether they're moving or at rest. They tie back to the overall theme of how forces influence everyday objects around us. Now let's look at what happens when two forces act on a body in opposite directions. If one of these forces is stronger than the other, the overall effect, or the resultant force, is not zero. These forces are what we call unbalanced forces. And the key point here is that unbalanced forces can change the state of the body, either making it start moving from rest, stop moving, or change its speed or direction. On the other hand, if both forces are equal in magnitude and act in opposite directions, then the resultant force is zero. These are called balanced forces. What's important about balanced forces is that they don't cause any change in the body's state of rest or motion. The body stays as it is, either at rest or moving uniformly in a straight line. So, in summary, balanced forces keep things steady, while unbalanced forces can cause movement or change in movement. This differentiation is fundamental to understanding how forces influence motion, and it ties directly into the overall theme of how forces work in our everyday experiences. Let's talk about how objects move when forces are involved. When an object is moving with a constant speed in a straight line, it will keep doing so as long as the forces acting on it are balanced. For example, if pushing force and frictional force are equal, the object won't accelerate or decelerate. But if an unbalanced force comes into play, like a stronger push or more friction, then the object's speed or direction will change. Now, here's the interesting part. If that unbalanced force is removed, the object doesn't just stop or change direction forever. Instead, it continues to move with the same speed it had when the unbalanced force disappeared. Think about a ball rolling on the ground. Initially, it rolls fast, but over time, friction slows it down until it stops. Similarly, if you stop pedaling a bicycle, it gradually slows down and eventually comes to a stop due to friction. This brings us to the key concept of friction itself. Friction is the force that opposes the motion of an object over a surface. It acts in the opposite direction of movement, resisting the motion and causing objects to slow down or stop. Understanding friction helps us explain everyday phenomena like why things slow down when we stop applying force. When a marble rolls down an inclined plane, its velocity increases as it gains speed due to gravity. Then, when it moves up on the second inclined plane, its velocity decreases because it's working against gravity. Now, if the inclinations of both planes are equal, the marble will reach the same height it initially rolled down from. This is because energy is conserved in this idealized situation, and no energy is lost. However, if we decrease the inclination of the second plane, the marble will have to travel a longer distance to reach that original height. Essentially, it needs more space to gain enough speed to climb back up. And if we set the second plane to be perfectly horizontal, the marble would keep moving forever, trying to reach the same height, but never quite getting there, because there's no component of gravity pulling it back down. This whole concept highlights an important point. An unbalanced force is needed to change the motion of the marble, like gravity pulling it down or up. But once the marble is in motion with constant speed on a level surface, no force is needed to keep it moving. This idea is fundamental to understanding motion and is closely related to Newton's first law. Now, relating this to Galileo's experiments, he was among the first to demonstrate that objects in motion tend to stay in motion unless acted upon by an external force. His work with inclined planes helped us understand these principles of motion and energy conservation in a very clear, experimental way. All right, let's take a closer look at Newton's laws of motion, starting with the third law. This one states that for every action, there is an equal and opposite reaction. So, whenever you push against something, that object pushes back with the same force in the opposite direction. It's a fundamental concept that explains a lot of everyday phenomena, from rockets launching to walking. Next, the second law tells us that force equals mass times acceleration. This means that the more mass an object has, the more force you'll need to move it or change its motion. Conversely, for a given force, a heavier object accelerates less. This law is really the backbone of how we understand motion in physics and engineering. And then, the first law, sometimes called the law of inertia. It says that an object at rest will stay at rest, and an object in motion will stay in motion at a constant velocity unless something else acts upon it, an unbalanced force. This principle explains why seat belts are so important. They help prevent us from continuing forward when a car suddenly stops. When we connect these laws to our overall theme, they illustrate how fundamental forces govern everything around us. They help us predict motion, design safer vehicles, and understand the universe at a deeper level. Newton's laws are truly the foundation of classical mechanics, shaping the way we see the physical world. All right, let's take a closer look at Newton's first law of motion. This law tells us that an object will stay at rest or keep moving in a straight line at a constant speed unless something forces it to change that state. Essentially, objects resist changes to their motion unless an external force acts upon them. This concept is fundamental because it highlights the idea of inertia, the tendency of objects to keep doing what they're already doing. It connects directly to the overall theme of understanding motion and the forces that influence it. So, in everyday life, when you see a ball just sitting still or rolling across the floor, it's obeying this very principle. Let's talk about inertia, which is basically the natural tendency of objects to stay in their current state. If an object is at rest, inertia keeps it at rest. If it's moving, inertia keeps it moving at a constant speed in a straight line. This is why the first law of motion is often called the law of inertia. It highlights how objects resist changes to their motion unless acted upon by an external force. Understanding inertia is fundamental because it helps us grasp how and why objects behave the way they do in different situations, connecting perfectly to the broader theme of how forces influence motion. Let's talk about inertia. Because of inertia, objects, including you, tend to resist changes in their motion. For example, if you're in a car going 80 km/h and it suddenly hits a brick wall, your body will keep moving forward at that same speed unless something else stops it. That's why wearing seat belts is so important. They help prevent injury by resisting that forward motion. Now imagine you're standing in a bus. When the bus suddenly starts moving, what happens? Your feet move forward with the bus, but your upper body tends to stay at rest because of inertia. That's why you might feel like you're falling backward. Here's another example. If you place a coin on a playing card over a tumbler and flick the card, the coin drops into the tumbler. Because of inertia of rest, the coin stays still initially, and when the card moves suddenly, the coin falls straight down into the tumbler. Think about traveling in a car. When the driver suddenly applies brakes, you feel yourself lurch forward. That's inertia of motion at work. Your body wants to keep moving forward even though the car is stopping. And here's a fun one. If you hit a pile of coins on a carom board with a striker, the lowest coin moves out first. Due to inertia of rest, the other coins tend to stay put and then fall down. So, as we've seen, inertia is all about resistance to change, whether it's starting to move, stopping, or altering motion in any way. It's a fundamental concept that explains many everyday experiences. So, the mass of a body is a measure of its inertia. Essentially, this means that the more massive an object is, the more resistant it is to changes in its motion. A body at rest will stay at rest, and a body in motion will continue moving at the same speed and in the same direction unless acted upon by an external force. This property, that resists changes in motion, is called inertia. Now, the key point here is that the amount of force needed to change a body's state depends on its inertia. If you want to start moving a heavy object, you need to apply a larger force. Conversely, a lighter object requires less force to get it moving or to stop it. This difference directly relates to the body's mass. The heavier the body, the greater its inertia. In the context of our overall theme, understanding inertia and mass helps us grasp why different objects behave differently under the same forces. It's a fundamental concept that underpins much of Newton's laws of motion. When a body is at rest, its velocity is zero, and as a result, its momentum is also zero. The SI unit used to measure momentum is the kilogram meter per second, which we often write as kgms or kgms to the power of -1. Now, the key formula for momentum is quite straightforward. It's equal to the mass of the body multiplied by its velocity. We write it as P equals m times v, or P equals mv. Here, P represents the momentum, m is the mass, and v is the velocity. Essentially, the momentum of a body is the product of how much mass it has and how fast it's moving. This concept is central because it links the physical quantity of mass and the motion, reinforcing the idea that momentum depends on both how heavy an object is and how quickly it's moving. So, understanding this relationship helps us analyze how objects behave when they move or collide, which is a fundamental theme in the study of physics. Now, let's take a closer look at Newton's second law of motion. It states that the rate of change of momentum of an object is proportional to the applied force, and importantly, it happens in the direction of that force. Essentially, this means that if you apply a force to an object, you will cause its momentum to change, and the bigger the force, the faster that change occurs. Think of it this way. If you push an object, the amount of push determines how quickly the object's motion changes. The direction of the force is crucial because it tells us which way the momentum will change. This law helps us understand not just how objects move, but how forces directly influence that movement, which ties back to our overall theme of understanding motion and interaction in the physical world. Let's look at how momentum changes. When an object accelerates, its momentum changes from p1 to p2. This change can be expressed as p2 minus p1, which simplifies to m times v minus u, or m times the change in velocity, v minus u. Now, moving on to the units involved. The SI unit of mass is the kilogram, and acceleration is measured in meters per second squared, or meters per second squared. From this, we see that the unit of force is kilogram meter per second squared, which we call a Newton, symbolized as N. Next, consider the final momentum of the object, which is P2 equals m times v. Combining this with the earlier idea, Newton's second law relates force to mass and acceleration. In fact, we often write it as F equals k times m times a, where k is a constant of proportionality. Usually, we simplify this to F equals m times a, which is the familiar form. This also means that the applied force F is proportional to the change in momentum over time. Since v minus u equals acceleration, we can write the force as proportional to m times v minus u, or more precisely, F equals k times m times v minus u. Finally, the rate of change of momentum is m times the change in velocity divided by the change in time, which is m times v minus u over t. So, in summary, if an object with mass m starts moving with an initial velocity u and is accelerated to velocity v in time t by applying a force F, then the force is directly related to the change in momentum, linking the concepts of force, mass, and acceleration in this elegant way. Newton's third law of motion is a fundamental concept that really helps us understand the interactions between objects. It states that for every action, there is an equal and opposite reaction. Now, what does that mean in practical terms? It means that whenever one object exerts a force on another, the second object exerts a force back on the first, and these forces are always equal in strength but opposite in direction. An important point to highlight here is that these forces act on two different bodies, so they are not canceling each other out because they're applied to separate objects. This concept is key to understanding how things move and interact in the physical world. Connecting this to the overall theme, Newton's third law reminds us that forces are always mutual. Whether it's a rocket launching, a swimmer pushing off the wall, or even you walking, these action-reaction pairs are at play, guiding the motion and behavior of objects around us. Let's consider two spring balances, A and B, connected together. Now, if we fix spring balance B to a rigid support and then pull on the free end of spring balance A, something interesting happens. Both spring balances show the same reading, meaning they experience the same force. This is a key point because it tells us that the force the spring balance exerts on B is exactly equal in magnitude to the force B exerts back on A, but importantly, These forces are in opposite directions. This observation demonstrates a fundamental principle. The force exerted by spring balance A on B is what we call the action force, and the force exerted by B on A is the reaction force. These two forces are always equal in size, but opposite in direction, which is what we refer to as the action-reaction pair. This experiment helps us clearly visualize that action and reaction forces are always equal and opposite, reinforcing the core idea behind Newton's third law. It ties directly into our overall theme of understanding how forces work in pairs, maintaining balance and symmetry in physical interactions. Let's look at some everyday examples of action and reaction. When a rocket is fired, the burning gases are expelled downward with a force, which we call the action. According to Newton's third law, an equal and opposite force is exerted on the rocket itself, pushing it upward. This is how rockets lift off. Similarly, think about a sailor jumping out of a boat. As he pushes backward on the boat responds with an equal and opposite force, causing the sailor to move forward and the boat to recoil slightly. Another example is when you release a balloon filled with air. The air rushing out downward exerts an action force, and the balloon is pushed upward in response, an easy way to see Newton's third law in action. And then there's firing a gun. When the bullet is propelled forward, it exerts an action force on the gun. In turn, the gun experiences an equal and opposite force, which we recognize as recoil. These examples all highlight a fundamental concept. For every action, there's an equal and opposite reaction. This principle explains how objects move and interact in so many situations around us, tying directly into the overall theme of understanding forces and motion. Thank you for your attention. So, as we see here, the momentum of the two balls before the collision is exactly equal to the momentum after the collision. This reflects the principle of conservation of momentum, meaning that the total momentum remains constant throughout the process. According to Newton's third law of motion, the force that ball exerts on ball B, which we call Fab, is equal in magnitude but opposite in direction to the force exerted by ball B on ball A, or Fba. This reciprocal force ensures that the forces are balanced during the collision. Now, when we look at the change in momentum of ball B during the collision, it's given by the difference between its final and initial momenta, mb vb minus mb ub. The rate at which this momentum changes, that is, the force exerted by ball B on ball A, is essentially this change divided by the time over which it happens, or mb divided by t. Similarly, for ball A, the change in momentum is ma va minus ma ua, and the force exerted by ball A on ball B can be expressed as ma divided by t. What's key here is that these forces are equal and opposite, aligning with Newton's third law, and they reflect how momentum is transferred during the collision. Putting all of this together, it shows that the total momentum of the system, the sum of both objects' momenta, is conserved. This leads us to the law of conservation of momentum, which states that the total momentum of two objects before collision is the same as after collision, as long as there are no unbalanced external forces acting on them. In essence, this law is a fundamental principle that underpins our understanding of interactions in physics, ensuring that momentum is conserved in isolated systems.